Hello, I welcome you all in this course on mechanical measurement systems. And today we will continue to discuss the first order system with frequency response. So, first order system. System for frequency response. When we were discussing the fundamentals of dynamic response of measuring instruments, then we had driven a generalized equation for frequency input between output and input as this is Bm minus 1 I omega m minus 1 plus B1 I omega plus BO, and this is about AO I omega raised to power n plus A n minus 1 I omega raised to power n minus 1 plus A1 I omega plus AO. This is AN. Now we are going to discuss, earlier we were discussing the step response or the ramp response or the impulse response of measuring first order instruments. Now this is frequency response. Suppose there is a sinusoidal input. How the system is going to behave? Shall the measuring system will also have output like this, or shall it have different type of output? Now, once we have sine input, then output amplitude is normally not more than input amplitude. I mean, amplitude reflects the energy of the wave. So, output amplitude is always less than input amplitude. That is one thing. Second thing is phase. Output and input, are they going to remain the same phase? Or output is going to be something like this. It is out of the phase, right? So there are two things in the frequency response. That is, first is amplitude ratio. So amplitude ratio, it is output amplitude divided by input amplitude. So if I want to draw the output response, I need two things. Frequency is going to remain same. If input frequency is 50 hertz, the output frequency will also be 50 hertz. Frequency will not change. Now frequency is constant. Now what is going to change? First is amplitude, and the amplitude ratio is expressed by K divided by 1 plus omega lambda whole square. Omega is frequency 2 pi f. Omega is 2 pi n radians per second. Right? N is the frequency. Suppose frequency is 50 hertz. So 100 pi is going to be the omega. And lambda is time constant. The time constant will reflect whether the response is sluggish or it is very quick in response. For large value of time constant, definitely the system response is sluggish. Once system response is sluggish, this is reflection of system response, and system response shall also be decided by the frequency. If frequency is high, right, you will find that there is a greater phase difference between input and output. Or when this lambda is high, greater difference between phase of inlet and output. So the phase is expressed by phi. So phase of output signal is phi is equal to tan inverse minus omega lambda. So it will always be lagging. Or phase lag can be written as minus tan inverse omega lambda. So in first order system, If we want to do the analysis of the first order system, there are only two things. One is amplitude ratio and another is phase lag or phase, right? And we will take some numerical problems one by one, and that will give you the clear insight how the system response is taken into account for a frequency input to the instrument. Now, first example is the temperature of air during a particular process is cycling at the rate of 1 cycle every 5 minutes. So, there is a air in the room and temperature is cycling 1 cycle for 5 minutes. Suppose air in this room, it is cycling with the rate of 1 cycle per 5 minutes. That is how the temperature is fluctuating. The temperature sensor has a time constant of 30 seconds. So, there is a temperature sensor in the room which has time constant of 30 seconds. Fine. What would be the variation in indicated temperature if the true temperature has sinusoidal variation of plus minus 50 degree? Plus minus 50 degree in a room, it is quite large. So, it is not happening in a building, it is happening somewhere else, where air temperature is varying between plus 50 degrees to minus 50 degrees centigrade, right? And the cycle is 1 cycle every 5 minutes, right? And the time constant of measuring instrument is 30 seconds. So, here we will have to find that what is the variation in indicated temperature. This is the actual variation, but what is the variation in indicated temperature by temperature sensing device? So, in order to find indicated temperature, first of all calculate the value of omega. So, omega is 2 pi n, 2 pi multiplied by n is 1 cycle every 5 minutes, 5 into 60, right? And this is going to be equal to 2 pi by 300 and 0.0209 radians per second. This is frequency or omega. The frequency is 1 cycle per minute and the value of omega is 0.0209. Now, response of temperature sensor. So, temperature sensor will also have sinusoidal response and the cycle time is again 1 cycle every 5 minutes. This is going to remain same, but amplitude will change. Now, amplitude of output divided by amplitude of input is equal to under root 1 by under root 1 plus omega square lambda whole square is equal to 1 by 1 plus 0.029 multiplied by lambda is 30 seconds multiplied by 30 whole square and under root. Fine. Now, in this case, the amplitude ratio is coming as AO by AI as 0.029 multiplied by 30 square plus 1 . This is not 0.0209. 209. So 0.0209 into 30 square plus 1.5. 0.847. It is 0.847. So amplitude of the response, amplitude of the frequency response is only 84.7, let us say, percent of input amplitude. So amplitude of output will reduce. Now what about the phase angle? The phase angle is tan inverse minus omega lambda is equal to minus tan inverse. Omega is 0.0209 and lambda is 30. And if we take minus of the tan inverse 30, it is going to be equal to minus 32.1 degree, not centigrade, degree. So this is phase lag. It's minus, so it is phase lag. Now, in this problem, it is being asked, determine the time by which the maximum reading of the thermometer lags the true maximum value. So, in a sine input, suppose this is the maximum value, but in response, we will get a different maximum value or maybe somewhere here. So, there is going to be a time lag. And this time lag can be calculated once we have the phase lag. Now, this phase lag, first of all, we will convert this into the radians. So, this phase lag 32.1 is converted into the radians. So, 32.1 multiplied by pi divided by 180 will give 0.56 radians. And we have omega radians per second, right? So this 56 0.56 divided by omega 0.0209, and this will give 26.79 or 26.8 seconds. So peak of input signal will be reflected in the measuring instrument after a lag of 26.8 seconds. Right. So in a frequency input, there are two things. One is amplitude ratio, and another is the phase lag. Now, regarding this, we will take another example. There is a first order instrument which is required to measure signals with frequency response of 100 hertz. Now, the frequency is quite high. 100 hertz. So n is equal to 100 cycles per second or 100 hertz. 100 hertz. If allowable inaccuracy in measurement of amplitude is 5%, allowable inaccuracy in is 5%, then measure the time constant. Then measure the time constant. What is the time constant? Allowable accuracy means allowable accuracy in amplitude ratio. So AO by AI is equal to, as we know, is equal to under root 1 plus omega lambda whole square. Now allowable accuracy is 5, because in first order system the system will not overshoot. So for input 1 we are not going to get 1.05. For input 1, for allowable accuracy here, it will be only 0.95. Omega is 2 pi n is equal to 2 pi multiplied by 100 is equal to 200 pi, and that is 628 radians per second. Now we will be putting the value omega here, 628. This AO by AI is known to us. The only unknown remaining here is lambda. Just with the help of these values, we will calculate the value of lambda, and lambda is 0.523 milliseconds. Now this lambda is 0.523 milliseconds here. Now phase angle. Now here the phase shift is required when frequency is 75 hertz as per the statement of the problem. So when the frequency, input frequency is 75 hertz, the phase lag or phase, we can calculate phase is equal to tan inverse minus omega lambda. So for new imposed frequency of 75 hertz, this is the phase or phase lag is tan inverse omega lambda, this is phase lag, and omega we can calculate from here, it is 2 pi f, so here itself we will calculate tan inverse 2 pi into 75 into lambda. Lambda we have already calculated 0.523 into 10 to power minus 3. Now for this value, the phase lag is coming as 13.84 degree. Now this degree will again be converted into the radians just by dividing by 180 and multiplying by pi, and the radian is 0.242. Once we have converted this phase lag into the radians, now omega is with us, we can find the value of time, that is phase lag 0.242 divided by 2 pi into 75, and this time is going to be 0.513 milliseconds. So in a frequency response of a system, always remember that the frequency of output and input remains same. There is a ratio of output amplitude and input amplitude, and output amplitude is also less than the input amplitude, and there is always a phase lag in the measurement. We can take another example where a thermocouple is having a time constant of 10 seconds. There is a thermocouple having a time constant of 10 seconds. Is used to measure the temperature of a furnace whose temperature fluctuates sinusoidally between, so if there is a furnace which temperature fluctuates sinusoidally between 500 degrees centigrade and 600 degrees centigrade. Okay, so mean value is 550. So around the 550 it fluctuates sinusoidally. This is 550, right? Now, and the time period is 60 seconds. Time period is 60 seconds. So capital T is 60 seconds for this frequency input. Determine the minimum and maximum value that will be indicated by the thermocouple. Again, now for this minimum and maximum value, thermocouple with time constant lambda, what is going to be the minimum and maximum value for temperature measurement? So first of all, we will calculate the value of omega. It is 2 pi by t. Here time period is given 60 seconds. So omega is 0.1047. T is equal to 60, we have put here 2 pi by 60, and this is the value of omega. It is radians per second. Now another value we require, lambda. Lambda is always is given here. So output, amplitude of output and amplitude of input is 1 by under root 1 plus 0.1047, that is omega, multiplied by lambda whole square. Now if we solve this, we will be getting 0.691. That is amplitude of input and output. Now this value and this value. Now this is the ratio of, so actual amplitude is 50. Actual amplitude is 50. Now this amplitude will be reduced by 50 multiplied by this plus 550, right? Because 550 is the average value, so this amplitude will be multiplied by this, right? And then we will add 550 here. So that is the upper value. Similarly, this amplitude 550 multiplied by this 550 minus this will give the lower value. So temperature will fluctuate in that range. So the range we can calculate. And phase angle, again calculate the phase angle and the corresponding time lag between temperature signals. So phase angle, again it is tan inverse omega lambda. So tan inverse 0.1047 into 10. This is the phase lag, and the phase lag is 46.32 degree. Now again this 46.32 degree will be converted into the radians, and these radians will again will be divided by rotational or this frequency input, and then we will be getting, or cyclic input, and then we will be getting the time. This is phase lag. Phase lag. There are two things. One is phase angle. The phase, actually it is a generalized solution. Phase angle is a generalized solution. Phase angle phi is equal to tan inverse minus omega lambda. But when we say phase lag, it is tan inverse omega lambda, because this is always minus tan inverse omega lambda. Okay. Now after this there is another problem for sine input. A first order system is having time constant of 0.25 seconds. So there is a first order system and it has sine input, and it is sine input is time constant is 0.25 seconds. And now the first order system is having a time constant of 0.25 seconds and has been subjected to a sine input giving the relationship theta I is equal to 0.25 sine 20t. This is the equation for input. Now we have to find the equation for output. So in order to find the output equation, we will calculate theta over theta I is equal to 1 by 1 plus omega lambda whole square. Lambda is here 0.25 seconds. Omega is sine omega t. Omega is 20. So we don't have to calculate from n. So simply we will take from here 20. Lambda we will take from here, and this theta O by theta I is equal to 0.196, or theta O is equal to 0.049. This is the amplitude of output. Now second thing is phi. So phi is tan inverse minus omega lambda, right? And when we take tan inverse minus omega lambda, and it is going to be equal to tan inverse minus omega is 20, lambda is 0.25, and from here we will calculate the value of phi. And because this phi is negative, so the theta O is going to be the modified amplitude AO sine 20t minus this value phi. Because it is plus phi, it is plus phi, because the value of phi is going to be negative. So this sign will change to negative to the absolute value of this, right? Now suppose the input to the instrument is not a simple sine wave, it is a combination of sine waves. Combination of sine waves means, now the input is sine 2t plus 0.3 sine 20t. This is input to the instrument. And time constant of the instrument is, let us say lambda is 0.2. Now, simply what we will do in this case, we will deal these two forms because they will be superimposed on each other. The actual wave you will find that is going to be, because here this is frequency is 10 times of this. This is omega t, this is omega 2, this is omega 20. Right? So, it means we will be getting waves something like this. Something like this if we superimpose these two waves. Now, here the amplitude is 1, here amplitude is 0.3. So, there is going to be substantial variation in this amplitude also. So, the ultimate waveform out of this equation is going to be like this. Now, we will deal each part of this problem as an individual problem. So, for this, for first one, so we will take, let us say QO by QI, let us take omega is equal to 2, right. So, amplitude is going to be 1 pi under root 1 plus lambda is 0.2, omega is 2 whole square, because it is 1 by 1 plus omega lambda whole square under root of. Now, if we solve this, we are going to get 0.93. Now, similarly, if we do QO by QI for omega is equal to 20, then we will get 1 by under root 1 plus 0.2 into 20. And this ratio is going to be 0.24. So, 0.32 it has come to ratio is 0.24. So, 0.3 will be multiplied by 0.24. For this output 1 will be multiplied by 0.93. Now, phi. Phi omega is equal to 2 is going to be tan inverse omega lambda. So, omega is 2 into 0.2 and that is going to be equal to 21.8 degree. And this phi for omega is equal to 20 is equal to minus tan inverse 20 into 0.2 and that is going to be equal to 76 degree. Right. Second thing is when we express this response, we always express in terms of m phi. So, ratio 93 and then 21.8, 0.24 m multiplied and within angle of phase is 76. Now, if I change this to 0.02, instead of lambda is 0.2, it is 0.02. Or let us take further 0.002. Then this amplitude ratio will improve. The amplitude ratio will become 0.999. This will now I'll use another color. Now, if I take 0.022 here, so this is replaced by 0.002 and this will be 0.999. Now, here also if I replace lambda by 0.002, it is also here also we are getting 0.999, right. And regarding the phi, this will be 0.002. So, it is going to be the tan inverse 0.002 into 0.2, 0.023. Similarly, this angle will also get changed. So we will be getting very close if a time constant is that low, 0.02. So output, say the response of the instrument is going to be the exactly same as the input nature of the signal, right? That is all for today. And from the next class, we will start with the dynamic response of second order system. Thank you.